Okay, so this video is going to be a little bit longer. We're going to deal with something that is a little abstract, and I've opened up a couple other tools that we're gonna use. So first of all, I want to talk about conformational analysis. All right. So we talked in a previous slide about how a conformation is the way that the angles of the bonds are with respect to each other. In fact, it's the dihedral angle that we're most interested in. Okay. So this is the torsional angle. That is the angle between these two hydrogens right here. And can you see, if you look straight down the axis of this bond, this is like a circle, right? Can you see a circle here? And there are 6 elements in the circle. They're all hydrogen atoms. And a circle, 360 degrees divided by 6 is 60. So yeah, that's 60-degree angle. This is a 60-degree dihedral angle between these two hydrogens here. All right. Now, again, let me remind you, and I pulled up another tool. I went online. Actually, let me close this down. I went online. Let me close this down and just show you how easy this is. I'm going to go online and I'm going to Google WebMO guest login. Guest login, because I don't want to pay a lot of money for WebMO. So the username is guest. The password is guest. It's the same thing. And I go on here and I go to new job, create new job. And I'm going to go to periodic table, make sure I got carbons. I do. I'm going to go carbon, carbon, right? I clicked and dragged there. Now I'm going to go, watch this. There's a couple ways you can do this. You can go here, hydrogens, 1, 2, 3. Obviously very bad angles, but we're going to clean this guy up, okay? So there's ethane, right? It's 2 carbons and 3 hydrogens each. Clean it up. Geometry, boom, all right? Now I'm going to turn this guy around. I'm going to come over here to this tool and turn it around. And I'm going a little too fast for you to get this, but I want to keep this video clean and simple. All right, so there's my ethane, right? And that's what we're looking at here. So let's come back over here to the PowerPoint. Okay, it looks like I've got 1 hydrogen that's pointing straight up on the atom that's closest to me and 2 that are pointing down. So let's go back over here to WebMO, and so it looks like I'm going to turn that. There you go. All right, so there's an atom, there's a hydrogen pointing up. There's 2 pointing down. They're at me, so I'm going to turn that to the side a little bit. Can you see that I got that? Okay. They're like that. All right. So this is the conformation that I have with, that. Now, in order for me to change this conformation, I'm going to do this a little bit fast, but watch. I'm going to select. You see this button right here? Select, click, 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 click. And it tells me I have a dihedral angle of -180. So watch this. I'm going to go to this button, which says adjust the dihedral angle. Click. And I'm going to go, oh, I don't want 180. I want, let's say, 60. Okay? So what that did now was that took those 2 atoms. Actually, I think that's going to look about the same. Let's go here. Yeah, it looks about the same, doesn't it? So I better do a different bond angle. I still have those atoms selected, those 4 atoms selected. Oops. Crud. I deselected them on accident. Click, click, click. And click. I'm going to go here. Let's don't do 60. Let's do 0. Watch this now. Aha! You see how these 2 are lined up with respect to each other? Watch. You see? Bam. Line straight up. Okay? This is going to give me something called steric strain, where these guys do not want to be lined up. They don't want to be lined up because they've got these big clouds of electrons around them, and that makes them collide with each other. There's actually a better reason than that, which is I don't want to get into in this course. All right? There's a much better reason than that, but we can, if you can just picture like a big balloon here and a big balloon here, and those balloons, they don't want to be close to each other, and they can get further away if we say take it to 60. Okay? Look at that. Now they got further away. We got more room for the big balloons. Okay? So let's go back over here. Don't forget that's what we're looking at. I know I'm taking some time here for this video. I warned you. So those 2 hydrogens are 60 degrees with respect to each other. Now, let's look at what this means. A staggered conformation is what I just showed you, okay? And an eclipse conformation is when they're right on top of each other. I also showed you that. I'm going to go back real quickly here and show it to you again. Let's go here. Let's say 0. Okay? And now they're eclipsed, right? Now, when we're drawing eclipse, obviously, if I was going to try to draw that artistically, that would be difficult because you wouldn't be able to see the hydrogens behind the other hydrogens, right? So whenever we're drawing eclipsed, we oftentimes offset them just a little bit. Can you see that? So when you see something that's offset like that, you can assume that the the artist, the one drawing it, the author of that figure is trying to draw an eclipsed conformation. All right, so this will be eclipsed, and that will be staggered. All right, now watch this. The torsion, the difference in energy between these conformations is 12 kilojoules per mole. What? What do you mean? Well, this is more stable than this. By how much? 12 kilojoules per mole. All right, so now what we're going to do is we're going to refer to graphs a lot, and we're going to go, look, if they're staggered, it's down here, the energy's here, and if they're eclipsed, they're up here. Okay? Now, if it's just ethane, then if that angle keeps turning, right? If that central angle there keeps turning, let me go back here. We're talking about that bond right there. If that bond keeps turning, you know, suppose you're holding these hydrogens there, and these other three hydrogens are turning constantly, like a propeller, right? Well, they're going to go through stages where this hydrogen is eclipsed with this one, right? The ones that are up now. And let me go. Let's suppose we move it 10 degrees at a time, okay? Now, can you see I'm moving that 10 degrees? Okay, let's do it. Let's do it at 20 degrees. That's 10 degrees at a time. Can you see what I'm doing here? 30 degrees, okay? 40 degrees. All right, they're not quite staggered. They look pretty staggered here, but if we take it actually to, oops, I lost my selection. Boom, 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 and boom. I think that's 40. Yeah, 40. Let's go straight to 60. And 60 is where it's all the way, okay? So let's go here. Okay, and that is staggered. So that's what's going on with this graph here. Now I want to show you something really interesting. This is a tool which is just, it's amazing. This tool you're looking at on the screen right now, it's just, I went to I Googled WebMO online guest. And there it is. And I come here, I went to File. I'm in the build molecule right now, but I created a new job, built a new molecule, and that's it. Now watch this. What I'm going to do is I'm going to calculate the energy for this. Calculate strain energy. And see, it's done automatically here. Do you see? I've got, wait, I'm going to clean this up a little bit. Now, I'm going to clean up geometry, okay? Cleaned it up. Now let's go to calculate strain energy. And do you see my total energy here is 2.3614. 2.3614 total energy. All right, just a second here. Let me go back here. Now that was kcals per mole, 2.3614, and I set up a spreadsheet that would automatically calculate from kilojoules per mole, or kilocalories to mole to kilojoules per mole, because your text is using kilojoules per mole. So I just put a formula here. I don't know if you're familiar with Excel or not, but I just said it's 4.814 times this cell up here. Okay, so it looks like it's about 10 kJs per mole, kilojoules per mole. Let's go back here again. And that's if it's staggered. You see that? Okay. Now let's see if it's, let's just change this. Oops, I gotta do it again. Boom, 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 and boom. Let's make that 0. 0. Okay. Calculate. Let's clean this up. Oops, nope. Took me back to lowest energy conformation. Don't want that. 0. Okay. Calculate strain energy. And it goes to 5.3093. That's the higher energy one, right? 5.3093 kcals per mole. I'm going to go back over here. 5.3093 kcals per mole. And look at that. This is amazing. So the one conformation was 2 kcals per mole. The next was 5. I converted those to kcals down here. And I took the difference, and it was 12. Look at this. This says that the difference is about 12 kjoules per mole. Can you see that? That's what's going on. As this guy's turning around, then as you can see, it's just hydrogen eclipsed with hydrogen, and it keeps turning, and then hydrogen is staggered, and then the next hydrogen is eclipsed with the next hydrogen, and so on. So that's what this is talking about. At 0 degrees, it's the highest energy, and then if we offset by 60, either negative or positive, it goes into its least energetic, its most stable, its least energetic conformation called staggered. All right. So having said that, I know this video is going kind of long, but it's just really valuable to be able to see that. So it turns out that this eclipsed is about 4 kilojoules per mole for each of these hydrogens eclipsing with each hydrogen, okay? Now, this is interesting. With a difference of 12 kJs per mole at room temperature, that's all the energy available at 21 or 22 degrees Celsius, 99% of the molecules will be in this staggered conformation. Obviously, if there was a bigger difference, then the percentage would be even greater, okay? Now, let's look at another molecule, propane. If we go off of there, I'm going to go back here, close, and I'm going to change one of these to a carbon. Boom. Now this is propane. I'm going to go ahead and clean up, add hydrogens. Okay, so what I got propane now. Now let's look down this bond angle. In order to do that, I'm going to go here. Okay. We'll try to get it in the same conformation as what's here. Okay. Let's go 0. 0 is where, yeah. So it looks like the methane is on the front. The methyl group is on the front. So let's go back here. Wait, where am I here? Let's go back here. Yep, and that's what I had, okay? So the methyl group, look at this. This is going to take some twisting and turning. You might want to do this with you really do want to do this with your model set too. It's going to take some time, so it's going to require some commitment on your part to do that. So I got my methyl group on front here. Actually, you know what I'm going to do? First thing I'm going to do is I'm going to clean this guy up. Nah, I'm going to leave it like that. Well, see, these hydrogens, right, they're not in a particular angle either. So it could be, yeah, that they're not perfect, right? But we're just going to do these bond energies anyway. So this is at 0 degrees. So I'm going to get my dihedral angle here. I'm going to select that one, that one, that one, and that one. You have to have 4 atoms to talk about with the angle between them. That one, that one, that one, and that one. Okay, oops, crud. That one, that one, that one. Okay, these 4 have a 0 degree bond angle, right? If I do that, remember, it's 0 degrees right there, okay? And that's what we're talking about with that first one. So now let's go here. It's 0 degrees, exactly. Let's go back here. That's at 0, okay? Now let's go all the way down to 60 and see how close it gets to 14. Now, I will tell you, if it's not right on 14, I don't stress about that because these calculators use different force fields. They use different models for how the atoms are supposed to act. So it might not be exactly 14. We'll figure that out in a second. 14 kJ, let's go. We're going to change it to 60, and then we're going to see how close that is to 14. Let's go back over here, and we're going to change it to 60. Boom. All right. And can you see that that now this methyl group right here is staggered with those 2 hydrogens back there, right? So let's see what the energy is. Oh, I forgot to calculate the energy the first time. I just hit Control Z. Let's take it back. Calculate strain energy. Looks like it's 148.844 kcals. 148.8. Was it 144? 844. I don't think so. Let's go back and look. 148.844. 148.844. All right, and let's now change it. I didn't say which was the higher energy, but we'll see in a second. Let's now go back here and change it. Close. Let's change it to 60, where it's staggered, okay? So can you see now that this methyl group over here is staggered with respect to those hydrogens behind it? Let's calculate, and it's 144. What? 144.1920? 144.1920. 144.1920. And it says it's 20 kJs. Look at that. 119. So this says 19, or 19.5. And this calculation, probably done with a different force field, says it's 14. But it's interesting how we can get close to that, right? What I didn't do was clean things up. I'm not going to do that right now because we're in the middle of a video. But what I could do is clean up geometry, mechanics optimize, right? That's one way to get the cleanest version of it. Let's see. Actually, I'm going to calculate. That's really easy to do. Let's calculate that real quickly. It's 1.4983. Wow, big difference. 1.4983. Let's don't do the math on that. I think you can see what I'm doing there, and I want to make sure we cover all of this information in as quickly as possible, right? So the torsional strain for propane now, is going to be also like this, because you've got this methyl group which is going around and eclipsing with a hydrogen, then it's staggered with a hydrogen, then it's eclipsed with a hydrogen, then it's staggered with a hydrogen. So it's going to have a similar energy profile.